So we're starting a new unit on radicals. The first thing we need to talk about is radicals are square roots, cube roots, things like that. So we need to remember, what are our perfect squares, perfect cubes, perfect fourths, that type of thing. So take a moment and see how many you remember. You can pause the video and then play it back if you want to. But our perfect squares, 1 squared is 1, 2 squared is 4, 3 squared, 9, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, and 10 squared. Those are the ones you should really know. And we could keep going with the list on and on. 121, 144. But if you know these, you've got a lot under your belt. What about perfect cubes? Ooh. 1 cubed, so 1 times 1 times 1. 2 cubed, 2 times 2 times 2. 3 cubed, 3 times 3 times 3. 4 cubed, basically it'd be 4 squared times another 4, so that's 64. 5 cubed, be 125, it'd be 25 times another 5. 6 cubed, 7 cubed. Most of these I don't know by heart, I'll be honest. And just if we wanted to continue the list, that'd be 512, 729, and then 10 cubed would be 1,000. And we could keep going with the list. 1 to the 4th power, 2 to the 4th power, 3 to the 4th power, 4 to the 4th power, 5 to the 4th power, and so forth. One of the other ways you could get to the 4th power is if I took a square and squared it. So 4 squared, 9 squared, 16 squared, 25 squared, and so forth. Now let's look at parts of what what we think of as a radical. So the radical symbol, radical sign, is this symbol. That's the radical sign. The number underneath is called the radicand. And there's a little bitty hidden number sitting inside that little hook that's called the index. Now normally we don't have a number there, and when there's no index there, we assume that it's 2. It's a square root. It's a 3, it's a cube root. 4, it's a 4th root. So some square roots, cube roots, some roots of radicals are really easy. The square root is 16. That means what times itself gives me 16? Well, that's a 4. The square root of 121. That's 11. The square root of 289. Ooh. If you didn't know this one, it's 17. You could check with your calculator. The square root of a fraction. Well, the square root of the numerator is 2, and the square root of the denominator is 5. So the square root of 4 over 25 would be 2 over 5. The cube root of 8, what times itself 3 times would give me 8? Well, that's 2. 343. So I listed that one out in here, and that's 7. 7 cubed is 343. But what about a negative number? Well, all of them would have to be negative. Negative, in this case, this would be a 5. So this is negative 5. What about a fraction? Well, to get a negative, my number would have to be negative, because a negative times a negative times a negative is a negative. And the cube root of 1 is 1. The cube root of 27 is 3. Now let's look at some fourth roots. The fourth root of 1 is 1. The fourth root of 2401. Oh, I didn't list that on my list. I should have continued this one. 6 to the fourth, 7 to the fourth is the 2401. 8 to the fourth is 4096. And I don't think I need to list anymore. So this is 7. 7 times 7 times 7 times 7. This one would be 8. And we'll learn how to do these in the calculator too. The fourth root of 81 would be a 3. And the fourth root of 16 would be a 2. So, if it's even, the index is even, a square root, a fourth root, and our radicand is positive, we are going to get real answers. And technically, if we really think about it, we could have had two options there, right? For each one of these, technically, we could have a plus or minus, right? So there's two. We only list the positive answer. What about if we have an odd? Well, we're going to get a real answer. And it's always going to be one positive answer. If we have an odd root and underneath is a negative, we get a real answer, and it's one negative. If we had a negative under the radical sign, the square root of a negative number is imaginary. Now, technically, we have two possibilities, a positive square root of a negative number or negative. We usually just list the positives. There are times where we're going to list the plus or minus, but when we're simplifying radicals, we are not. So, when we're simplifying radicals, what we're trying to do is simplifying radicals. There should be no perfect squares or cubes, etc. in the radicand. We want it as simplified as possible. Now 117, I'm not quite sure about that one. So one way to do this, I'm going to show you on a calculator. It's a square root. So what I'm looking for are perfect squares. I want to make sure there's no perfect squares underneath. So I have my list of perfect squares up here, and I've got 117. So I know 100 doesn't go into 117. I could take 117 divided by 81. Doesn't go in evenly. Divided by, next one is 49. Divided by 25. I know that's not going to go in, right? Because it's not divisible by 5. It's not even, so I'm really not thinking 16 is a good idea. So 9 is a factor of 117. In other words, I can rewrite 117 as 9 times 13. And furthermore, that would be the square root of 9 times the square root of 13. I know the square root of 9. That's 3. 13 is not a perfect square, so it stays under. Square root again. So I'm looking for perfect squares inside of 320. 320 is kind of big, and I know it's not divisible by 100. And I don't think 81 is going to be a good option. And you can, whoops, let's try 64. Oh, 320 is 64 times 5. Cool. So I can rewrite this as the square root of 64 times the square root of 5. Square root of 64 is 8. So 4 times 8 is 32 square roots of 5. What about 48? Ooh, I know 48. 48 is 8 times 6. Okay, and 8 was one of those perfect cubes we listed out. So this can be the cube root of 8 times the cube root of 6. The cube root of 8 is 2. So 2 times 2 is 4 on the outside. My video is being choppy today. Sorry about that. Cube root of 6. Ooh, 108. Let's see, 108. And we're looking at cube roots. So 108 divided by, 125 is too big. Not that. Divided by 27. Cool. I got 27 gives me 4. So 108 divided by 27 is 4. So I'm taking out 27 from the cube root, splitting it up to 27 times 4. The reason I'm doing that is 27 is one of those perfect cubes. The cube root of 27 is 3. Now there was a 3 out there. 4 is not a perfect cube. He has to stay under. 3 times 3 is 9 cube roots of 4. Cube root of negative 250. So in the earlier example, we had 125, negative 125. So notice I could rewrite this as negative 125 times 2. 2 times 125 is 250. And the cube root of negative 125 is negative 5. Cube root of 2. Cube root of negative 2. Be careful. As soon as I saw this, I thought to myself, oh, it's an imaginary answer. It's I. It's not. Cube root, I could separate that into the cube root of negative 1 times the cube root of 2. And negative 1 was a perfect, 1 is a perfect cube. So this would be negative 1 times negative 1 times negative 1. So 6 times negative 1 cube root of 2. That gives me negative 6 cube roots of 2. So again, you're looking for those perfect squares, perfect cubes, perfect whatevers, and we made a list of them. So 162, I think that's 81 times 2. Cool. Because 81 was on that perfect fourths list. Whoops, that's a fourth, sorry. fourth root of 2. 81 times 2 is 162. The fourth root of 81 is 3. So I've got 3 times 3, fourth root of 2. 3 times 3 is 9, fourth roots of 2. 2592. Woo! I may have to play with this one a little bit. So 2592 divided by 2. I know it's even, so I'm going to start there. 1296. That was on my list. That was the 6 to the 4th. One, 2, 9, 6 times 2 is 2592. The fourth root of 1296 is 6. And so that's 30 fourth roots of 2. Now what if we have variables under the radical sign in the radicand? What we're going to look for is exponents under a square root that are multiples of 2, because those would be perfect squares. Cube roots, we're looking for cubes, and fourth roots, I'm looking for 4s. So let me show you how we can split this up. First off, the number 32. 32 is 16 times 2. So I'm going to start by separating this into 16 and 2. Exponents, I'm looking for multiples of 2. Okay, so I'm going to have, well, that is a multiple of 2. That's okay. Y to the 9th, I'm going to rewrite that as y to the 8th times y to the 1 power, because 8 plus 1 is 9. The square root of 16 is 4. So I'm going to take all the ones that are perfect squares out first. So perfect square 16 is 4. The square root of x to the 4th is going to be x squared, because x squared times x squared is x to the 4th. The square root of y to the 8th is going to be y to the 4th. And notice the ones that we left unmarked. They have to stay under the square root sign. So there was a 2 and a y that have to stay in jail. 324. Whoo. Wait, 324 I think is actually a perfect square, and I'm going to test that theory. 324 is 18 squared. See, 324, square root of 324 is 18. So that's cool. A cubed, I'm going to write that as a squared. So the square root of a squared times the square root of a. I'm going to make that be b to the 6th times b. The square root of 324 I just showed you was 18. The square root of a squared is a. Here's another multiple of 2. So this is going to be b cubed. The square root of b to the 6th is going to be b cubed. And the ones left under are a and b. I forgot to box my answers. Cube roots. Cube root of 216. Oh, that's easy. That's 8. Cube root of m cubed is m. The cube root of n to the 6th is n squared. Uh-oh, I'm going to have to break this one down. 56. 56 is divisible by 8. And it's 8 times 7. So I'm going to break that down into the cube root of 8 times the cube root of 7. Looking for multiples of 3, because my index is a 3. So one thing you could do, if you have trouble with this, I could write this as r, oops, cube root, I forgot the cube root symbol, r cubed, it's up to 6 of them, right? And then r squared, 3, 6, 7, 8, okay. And then cube root of s cubed, cube root of s to the third, and another s. All of the perfect cubes get taken out. So the cube root of 8 is 2. Here's going to be an r and another r, that's r squared. S gets to come out. Underneath the cube root symbol, I still have a 7, r squared, and a s. Negative 64. Oh, 64, that's 4 cubed. Cool. So that is a perfect cube. X to the 10th. If we're thinking about multiples of 3, I could write that as x to the 9th and another x. 21 is a multiple of 3. See if you notice anything here. The cube root of negative 64 will be negative 4. The cube root of x to the 9th is going to be x to the 3rd. There are 3 sets of 3's. In 21, there are 7 sets of 3's. So this is going to be y to the 7th that gets to come out. It's almost like I took 9 divided by 3, 21 divided by 3. Negative 81. Ooh, okay, so that's a multiple of 3. 27. Negative 27 times 3. I can't break p squared into an exponent that's a multiple of 3, so it's just got to stay there. This is a multiple of 3. The cube root of negative 27 is negative 3. Can't take the cube root of that. Can't take the cube root of that. I can of this. So there's a little shortcut here. If this is a multiple of 3, 12 divided by 3 gives me an exponent of 4. That only works when we're dealing with exponents. 3p squared has to stay under. I keep forgetting to box the final answers. Okay, multiples of 4. So w to the 4th is a multiple of 4. This could be written as v to the 16th with another v. The 4th root of w to the 4th would be w. The 4th root of v to the 16th would be v to the 4th. So we took the 4th roots of those. This one's still under, so he has to stay in jail. On this next one, I want to kind of show you an alternative method. If this is making you struggle too much. 48. Let's break down 48. 2 and 24. 2 and 12. 2 and 6. 2 and 3. So notice that I have these 4 2's. That's like having 2 to the 4th. So I could rewrite this as 2 to the 4th times a 3 is left over, m to the 8th, that's a multiple of 4, that's okay, and n to the 3rd. This is a power of 4, so the 4th root of 2 to the 4th would just be a 2. It gets to come out of jail. This one has a power that's a multiple of 4, so the cube root of m to the 8th will be m squared. The other two do not have an exponent that's a multiple of 4, so they have to stay under. $625. $625. I know that's a multiple of 5. So if you are if this is kind of confusing you, if you're not good with your powers, you can always make one of these tree diagrams. So I took 625 divided by 5 and got 125. And then 125 divided by 5 and got 5 and 25. Oh, and 25 is 5 times 5. So notice that 625 can be divided up into 5 times 5 times 5 times 5. So I can rewrite 625 as 5 to the 4th, looking for exponents of 4, or that are divisible by 4, multiples of 4. So 23, I could write that as c to the 20th and c to the 3. Multiples of 4, d to the 8th and d to the 3. 8 plus 3 is 11. The 4th root of 5 to the 4th would just be a 5. He gets to come out of jail. The 4th root of c to the 20th is going to be c to the 5th. Come out of jail. The next one that's a multiple of 4 is d to the 8th, so that's d squared. Anything that's not marked out stays in jail. Notice on this last one that we have y plus 3 in parentheses, and the exponent is a multiple of 4. So the 4th root of all that to the 8th power is just going to be all that to the 2nd power. Or, couldn't I write that a different way? If I multiplied y plus 3 times y plus 3, just to remind ourselves, you would get y squared plus 6y plus 9.